Hello dear, and welcome back to my channel. In this video we'll start solving problems based on the 01 knapsack topic we have just started discussing. This example would be to find the longest common subsequence using using ideas from the 01 knapsack. Let's just take some examples. Let's say we have two words. Let's say the first word apple, the second word pineapple. This is a very trivial example. We can already see the common subsequence, apple, apple, here. We already see the common subsequence. Very trivial. But how, supposing we have other examples that are not this trivial, how do we find the longest common subsequence? And in this example, we know that the common subsequence, apple and its length, there are 5. So the longest common subsequence of these two words is 5. Like I said, this is very trivial. We can see it just by looking at it. But for not so trivial examples, how, like the one I have by the side here, this is X, this is Y, this is not so trivial. How are we going to figure out how to get the longest common subsequence? So in this video, we would be looking at how to solve this problem recursively and how to solve it using dynamic programming. And that's because dynamic programming will help us solve it faster. So for solving problems like this, if we can say that we start from the last letters of the two words in consideration, if the last letters are the same, what we do, we cross them out and count +1. If the last letters again are the same, count them out, now it's +2. The last letters again are the same, count them out, now it's +3. We continue like that. But like I said, this is a trivial example. We have 5 is the length of the longest common subsequence. What happens if the last letters are not the same? What happens? So when the letters are not the same, let's say we have apple and we have pine. Oh, okay, this is the same, so we cross it out, we have 1. But L is not N. So what do we do? Maybe you can pause this video and think about it for a second. How do you think we can figure out what the length of the longest common subsequence would be if the last alphabets are not the same? So for this, we can, when we pick up the first letter, the first word, the remnant of the first word, APPL, then we can pick up this one, PI. We check whether at this point we find common subsequence. If we don't, we check for this APP and pin. We consider. So what we do is we put the two words side by side, and then in the first, we are going to consider 2 cases now. For the first consideration, we consider the first remnant, the remnant of the first word in full. But then for the second word, we are going to consider it except the last letter. Then we do the same for the second case, but in the second case we do the inverse. We consider the remnant of the first word with the exception of the last letter. But then for the second word, we consider everything. So that's how we keep considering, and for each stage we choose the maximum. We choose the maximum subsequence. So let's write down this recursive structure more formally. So let's say we have X, we have Y, and we have M and N. where m and n tells us the length of x and y. So if let's start, if m is equals 0 or n is equal 0, that's if m and n is equal 0, I'm just going to write this down. If this is equal 0, we return 0. That's if the length for, if there is nothing for the words x and y, that if there is no word, I think that's just the way to say it. If there is no word, if it's blank, at the point where there is no other word remaining, we return 0. That means nothing is remaining, right? That's an easy way to say that. And if, let's say that x m minus 1, when we skip out the very last word of x, is equals y n minus 1, that is, in this case, the last letters are the same. When this is the same, we want to return, when the last letters are the same, we want to return 1 plus whatever it is that's remaining. We have x, y, m minus 1, n minus 1. This is for when the last letters of the both words are the same. If they are the same, you return this. You could just put this. But if they aren't, else we want to return the maximum, just like I said. We want to return the maximum, whichever it is that has the maximum value. That's what we return. X, y, m minus 1, n. So we return the maximum for this. So I want to grab this copy. Let's move forward. So let's consider an example with this. Let's consider this. Let's say we have these two words, x and y. It's not so trivial, so it will make for a good example. So let's say this is like a function, right, for the longest common subsequence for x and for y. Let's call this x, and for y. So we start off. So the first thing we do is we look at the two words. Are the last letters the same? They are not. This is B and this is A. So what we do is we have two scenarios to consider. We want to consider this A, B, C, B, D, A, B. We want to consider this B, D, C, A, B. We want to consider this, or we want to consider this A, B, C, B, D, A, and B, C, B, D, C, A, B, A. So we want to consider this. These are the two different scenarios we consider, and we go again. So we see that this is already a recursive substructure. Yes, the last letters are the same. So what happens when the last letter is the same? We have A, B, C, B, D, A, B, D, C, A plus 1. That's what we have. So we have, let's put this down. So when these are the same, for the sake of space, I'm just gonna, this would be A, B, C, B, D, A. This crosses out because they are the same. So we have, what we have under consideration now is B, D, C, A, everything here, plus 1. So this is what we have under consideration. And what happens here, the last letters are the same, so exactly the same scenario here plays out. The remnant plus 1, and we see here the last letters here are still the same, so we would still write out the remnant plus 2. So we would continue that way until there is nothing else. So that's the recursive substructure of what this problem looks like. First of all, we put it down in form of an algorithm. If we were to write this recursive substructure in form of an algorithm, this is what it would look like. And if we were to draw the recursive substructure, this is what it would be. You can take your time to expand it to the end, but you have a good idea of what it looks like. So now let's doing this will take a lot of time. So to make our job easier, let's consider solving this problem using dynamic programming. Still using the same formula we have discovered from our recursive structure, or in the recursive algorithm. So let's say that this is a array. So we have I comma j, this is comma j. So this would be the maximum length of a longest common substructure of a given word x and another given word y. Given word, yeah, I, j, yeah. So let's still, this is still derived from everything we've talked about before now. I comma j, so it's either we have, let's say, if the last alphabets are the same, this is the case. We have I minus 1, j minus 1 plus 1. This is what we have when xi is equals yi. And if not, we find the maximum. So at this point, we are going to take a very interesting example to see how this plays out. For we want to find the maximum between this minus 1 and j. So we're going to find the maximum between these two, and this happens when this is not equals, oh, this is j, is not equals this. So we're going to, like I said, look at a very interesting example, how to work this out. So we have a table that looks like this, a straight table. If you like this video, please remember to subscribe and share with your friends.